So today we are talking some more about drawing Euler circuits and paths. Last time we talked about drawing Euler circuits. I just want to do a few more examples of that, and then we'll also talk about paths. Drawing Euler circuits and paths. All right, so we discussed last time what is called Fleury's algorithm. This is for drawing an Euler circuit. It says so what we're trying to do here is I show you a graph, and then your job is to draw an Euler circuit in the graph. Remember, that means it is a circuit which covers every edge without repeating any edges. And the way to do this for circuits is you can start at any vertex, and you make a path using any edges you like. So there's a lot of freedom when you do this, and in a typical problem, your answer is going to look completely different from everybody else's answer because of the choices you make along the way. But you make a path choosing any edges except you never use an edge. This is a somewhat complicated part. You never use an edge which makes a bridge among the unused part. All right, and this is called Fleury's algorithm. This is how I said it last time. Another way of thinking about this, I don't know if this sounds confusing to you. Another way of thinking about it is never allow the unused part to become disconnected. This is another way of saying the same thing that I just said up there. Never allow the unused part of the graph to become disconnected. That's the same as saying never use a bridge. Remember, a bridge is an edge which would make the graph disconnected if you were to take it away. So as you're choosing the edges from one to the next, you have to keep in mind what are all the edges that I didn't use yet, and you have to make sure that you're always keeping those unused edges connected together. Other than that, you can choose pretty much whatever edges you like to make your circuit. So for example, this is an example. Ooh, trying to make a nice circle here. This is a nice example that we did last time. Something like that. All right. Let's draw an Euler circuit. So I said, I scrolled it, start at any vertex, make a path using any edges except never use an edge which makes a bridge. Okay, so I'm going to start here, say. As I was walking around trying to help folks out, a big issue that I saw when I was just walking around seeing people do this is they're like, I don't know which way to go. And the answer is you can usually go whatever way you like. It's just you have to make sure that all the edges you didn't use yet, they stay connected, and they are connected in this case. So maybe I'll go this way first. There's just like a lot of freedom to choose whatever edges you like. I just picked those to begin with. Am I doing okay so far? The question is, are all of the ones that I didn't use yet still connected together? And maybe I'll use my fancy line here. Look at all the ones I didn't use yet. You have to be able to look at this and focus on just the ones I didn't use. They would be here, like all of those I didn't use. And are they connected? At this point, yes, they are. So I haven't made any bad choices yet. You just have to make sure all the ones you didn't use yet stay as a connected graph. They're not like in two separate pieces. All right, but for example, if you're copying this down, don't do this, what I'm about to do. If I did, I'm trying to do an example of doing a bad choice. How about this? If I continued in this way, actually this is still not a bad choice. I'm not sure it's even possible to make a bad choice in this example graph. Anyway, let's just continue. So from here, I could, trying to keep all of this other stuff together, maybe I'll go up the top here and around this way, right? Now this stuff which I haven't used, I'm trying to keep track of this in my head as I go. But that's the stuff I haven't used yet, and it's still connected together, so I can continue maybe this way, down here. In this particular example, there's not much you could do that would mess it up. But anyway, there we go. I came back to the beginning. I used every edge once without making any repetitions of any of the edges. So this is an Euler circuit. All right. Let's just try a few more of these, and then I have some more kind of bigger ones for you to try. And also, we should talk about Euler paths rather than circuits. Here's another one where I would like to draw an Euler circuit. Something like that. All right, again, you can start wherever you like. So maybe I'll start in the middle. When you're drawing this for me, you should try and somehow make it obvious where your starting and ending point is, just so that I can tell. Just making a giant dot is probably good enough. And then I'm going to draw my circuit. Again, you can usually do pretty much whatever you like. You just have to make sure that the edges that you have not used yet remain connected. So maybe I'll go up first and then down the side like this. All right. Keeping in mind where are the edges that I haven't used yet. At this point, they're like here, here, and there, right? And that bunch of blue stuff is still connected together. So I'm feeling good about this so far. Maybe now I will go around the bend here across the bottom, and then up the side and back down this one. Make sure you don't reuse any of the edges. That, of course, is not legal in a Euler circuit. All right, and then I think where are the ones I haven't used? It's really only that and that at this point, and so we should just go straight across that those ones. Straight across here and back up to the middle. There you go. All right. My red line is a little sloppy. I'm not following the graph lines exactly, but there's a good reason for that. It won't make any sense after the fact if you try to follow the lines exactly, as I discussed in detail last time. All right. Any thoughts about these ones so far? These were kind of easy ones in my opinion. Actually, in these two examples, there's not much that you could do to mess it up. Let's talk about, you can do this also for Euler paths. So for an Euler path, the only difference there is that the start and end point are different, are, two different vertices, right? The ones that I was just doing have all been Euler circuits, which start and end at the same point. But for an Euler path, the start and the end point are two different vertices. And if you recall the rule about when an Euler path exists, an Euler path exists when there are two odd vertices and the rest are even, right? And the starting and ending point are two different vertices. Those must be the odd degree ones, right? But anyway, you do the same procedure. So you do the same, I'll just say Fleury's algorithm. Fleury's algorithm works the same way. The only difference is you have to be sure to start at one of the proper starting points, and that is the two odd degree vertices. So Fleury's algorithm works the same way, but you must start at an odd degree vertex. And you have to finish at the other odd degree vertex. Remember, if there is an Euler path, it means that all the vertices are even degree except for two odds. And you have to start at one of the odds and finish at the other odd. So you must start at an odd degree vertex. And if you do it right, you will automatically end up at the other odd. Actually, you don't have to try to make it to the ending point, the proper ending point. You have to choose a legal starting point, but if you do everything properly, you will just magically make it to the end point, which is kind of satisfying. So you will automatically end at the other odd degree vertex. Welcome. All right, you will automatically end at the other odd degree vertex. Let's just try one like that. So here is one. This is similar to one I just did a few moments ago, but it has like one less edge in it. And your job is find an Euler path. Find and draw an Euler path. All right, so I'm going to do the same thing. The only difference is you have to be sure, I said, must start at an odd degree vertex. So if I'm asking you to draw an Euler path, you have to first decide what all the degrees are so that you can find the two odds. And the two odds will be one of them will be the starting point and the other will be the ending point. So I'm going to write in all the degrees, and I hope everybody feels good about writing the degrees at this point. That's a 2 in the upper left. Right in the middle here is a 3. This is a 2. This one is a 4 because there are 4 edges touching that vertex. That's a 2. The bottom is a 4. In the middle is a 4. In the corner is a 2, and there's another 3. All right? Those are all the degrees for this graph. And because I'm talking about Euler paths, I am fixated on the odd ones. Those are the important ones for the sake of an Euler path. And those 2 that I circled must be the starting point and the ending point. And actually, it's sort of up to you. You can decide to start either at the top one or at the left one. And then if you do everything right, you will automatically end up at the other. So you must start at one of the odds. This is really the only difference when it comes to path versus circuit. You must start at one of the odds, and then if you do everything properly, time to go to class. If you must start at one of the odds, and then if you do everything properly, you will automatically end up at the other. Let's just try it out. So how about we start at the top? I'm going to start here. And as before, you can pretty much do whatever you like as long as the ones that you haven't covered yet remain connected at all times. So maybe I'll go over to the left first. And then I guess I have to go down here. Now, don't be worried about sort of arriving too soon at the end. I am going to arrive at, that is the point where I'm eventually going to stop. But of course, I'm not done yet. So you can either from here go straight down or across to the right. And I don't think it matters either way. Maybe I'll go straight down through there. All right. Remember, as you're doing this, you are paying attention to all the ones that I did not, all the edges that I didn't use yet, which would be here at this point. And those are all, oh, it disappeared. Those are all still connected together, so I'm feeling good at this point. Keep on picking edges. From here, I don't think it matters which way I'm going to go, so maybe I'll just go straight across the bottom. Maybe I'll do this little triangle here, and then come up to the middle. And now what I have, the unused ones right now look like this, which is still connected together. And so I'm still feeling good. You could go straight up through the middle, or you could turn right here. I don't think it matters which way. Maybe I will turn right and then go up and around this business. Back to the middle, and over here, finally finishing off at the other odd. Like I said, you don't really have to try to make it to the ending point. You will, if you're doing it properly, you will just automatically get there. Maybe on these ones you could write a little start and end. Although I think it's pretty clear following my my line here, you can tell where I started and where I ended up because of the arrows. All right, I have some for you coughers to try. Let's try. I actually have 2 sort of big ones. Big ones are a little more interesting because there is a little more opportunity to get yourself messed up in a big one. So I hope you can draw. Sometimes the hardest part is just like copying down my big pictures. Here is a big one. I got squares inside of squares here. This is my big one. All right. Your job is draw an Euler circuit or path. I will say whichever is possible. So you should start by thinking, first of all, is it going to be a circuit or a path? And then this will determine where you start. If you intend to draw a circuit, you can start wherever you like. If you intend to draw a path, you must begin at one of the odds. All right? And then I have another one. That's another sort of big and complicated picture. All right, that's my second one. So your the first thing you do for the first one should be figure out what all the degrees are so that you can tell if it's going to be a circuit or a path, and then see if you can draw it in. You may find these to be easier if you draw big. I see a lot of people drawing little guys on your paper, which is all right, but it'll be easier if it's big. Big it up. looks great. Yeah. Doing okay? I think so. So you can do a circuit or a path. Right? And you have to start at you have to start at one of the outs.
I was going to draw it.
Okay. Good so far. What we're going here. This is pretty good. Can I make it just these arrows? They should like here. They should connect. It doesn't really matter here, but it matters for instance here because like this one comes in here and then where does it go out there? I can't tell on the picture. Like, is it that one or is it that one? So if you which one of them? Yeah, it's like that. That's what I wanted. So we have some draw a picture. There's some stuff here. That's what your graph is disconnected, which is just 2 edges. How's it going? This looks pretty good. Actually.
Yeah.
Yeah, actually it does. This is a little better. Yeah, you didn't cover some.
Yeah.
Doing okay? You got the first one all right?
Yeah.
Yeah, that's good. Great. How's it going? Satisfied with the first one? Yeah, great. You okay? Okay. So far. Still doing okay? This still good here? Good first one already? The numbers, yeah, great. So you know where you're gonna start. So if you see the 2 odds, that means you have to go to the path, not a circle, because there's 2 odds, and you should start at one of the odds and end at the other path. Yeah, I think you miss all these edges. Where are you now? The problem is you use all these diagonal lines, which means from here you can never get back to this color. So you should use one of these diagonals so that you can do all this stuff. How's it going? It's looking okay. Yeah, I see you missed this. Yeah, the ones that you didn't use yet includes those. Where are you sitting at? Yeah, so I would say instead of coming back here, you should. Still okay here? How's it going here? Yeah, this is alright. Yeah, your arrows should go. Did you start here?
Oh, yeah,
Oh,
I've been
okay,
trying
great.
different.
Can I make an artistic comment here?
Sure.
These arrows are not, it's not possible for me to tell what where did you start? That one? Okay, and then the first thing you did was down here,
Mhm.
across here. Now, actually, I can't even tell, but went to there. But then you go up these arrows. Yeah, it does, your picture doesn't indicate that. So
Okay.
that's why when I draw my lines, they're kind of next to the edges, and it looks a little sloppy because I'm trying to clean it up like this now. It's not.
Okay.
How's it going?
Good. I forgot my cross in the middle here, so I didn't do that. But without it, it looks great.
Okay, yeah.
Yeah. So I just have to go back and add that.
Seems weird with your numbers.
Okay. Let's see. Oh, that was because before I didn't have the
Oh, you
cross.
just didn't draw it in there before?
Yeah.
Okay, then
So
I think
I just drew
I
it
think
in
it's
now.
correct.
Okay.
Without
Without-
that, then
Thank you.
how's it going? I'm drawing. So where did you start here? Started off this, there's two groups. Just so these arrows should have an arrow and then an arrow. Yeah, and like this one, I think it actually connect them. Yeah, that's a lot better. How's it going?
Good.
Still good? All right.
Can we talk about these? I know not everybody is done. At least everybody has drawn the pictures. I find that it takes a long time just to draw the picture sometimes. Maybe I should have printed these out, these big ones. Anyway, this is the first one. So you should first of all look at all the degrees and identify that there are two odds and they are here and here. Everybody did that eventually. So those are both degree 3. So I have to start at one of those and end at the other one. And as usual, you can more or less choose whatever edges you like as you go around. So I'm going to start here. And I'll end down here. Maybe I'll go across to the left first and then down this edge. I saw people immediately getting screwed if you decided to go down this diagonal and then immediately back up the other one. That is a bad idea. That's because at this point, if I look at all the parts, all the edges which I didn't cover yet, it would be here and also here, like so. And you will see those two blue regions that I just drew are actually disconnected. There's one on the inside and one around the outside. And this means that I have chosen a bridge in the graph, which is a bad idea. So I should not have done, actually the problem is like right here. Coming out this way and then immediately going back means I am now cut off from this stuff out here. So I'm gonna backtrack a little bit. It's a lot easier for me to just take a few steps away. So anyway, having gone out here, I'm gonna now try and do all of this outer stuff. Maybe I'll come around here. I'll do this square, and then I'll go around the big square. As you're drawing these, make sure that your line is actually readable. I hope that it's not so hard to see where my line goes from one step to the next. As I was walking around, I saw many of you were disobeying my commands from last time about don't draw the line going right through the vertices. It will be impossible to read after the fact. And don't just draw a bunch of disconnected arrows either. These are also impossible to read after the fact. Anyway, to finish off, I am now going to come back into the center region here and then just cover all of this business in the middle. Maybe I'll do that. This little bow tie kind of a shape. There you go. I finished at the end point. So this is how I did it. Your answer almost certainly is not exactly the same as mine, but I hope it's something like that. Anybody got questions about that? These can be a little tricky and frustrating. If you mess it up, you will have to redo it, probably. All right, Okay, how about this this other big one? Some people didn't even get started on this one, which is fine, but you should, again, start by looking at the degrees and seeing if they're all even. That means I'm going to make a circuit, or if two of them are odd, that means I'm going to make a path. And if you look closely at this one, you will find an odd right here. That's a degree 3. And an odd right here. That's a degree 3. Everything else in this graph is even degree. And so I'm going to make a path which goes from one of them 3s as the starting point. Maybe I'll start here. And then I'm going to end up at this other one. All right? And we just do as we usually do. I'm going to try not to think too hard about this, just choosing edges as we go. Make sure that you don't repeat any edges. And make sure that the region of edges that you haven't hit yet always remains connected. So like right now, I will check in and make sure. All the ones I didn't hit yet is here, all of this stuff, and here, not that last one, but here, right? Anyway, all of that stuff is still connected together. I haven't broken it into 2 pieces, so I'm still feeling good at this point. I will continue my red line then. Maybe go down, across the bottom here, across the bottom here, all the way over here. I am just making this up as I go along, making sure that, again, all the stuff that I didn't cover yet, all the edges that I did not cover, is this stuff, which is still all connected. Oops, not that, I already did cover that last one. But anyway, all of this blue region is still connected. It's not in 2 separate pieces, so I'm still feeling good about how I'm doing. All right, I will, continue. How about all the way across the top, down this guy, across here. Now I gotta cover a bunch of this stuff. I always feel a little self-conscious doing this in public and having to say something while I'm doing it. I go over here, now I go down here, now I go over here. It sounds stupid to me, but I also feel like I shouldn't just like do this in silence, even though. Anyway, I did it. All right. I covered all the edges and ended up at the end there. You can make sort of like vroom vroom car noises while you do it if you like. That's that can be fun sometimes. You know, just have fun with it. Don't be afraid to be quirky. All right. This is my answer. Like I said, you know, your answer is almost certainly going to be different from mine. There are many possible answers. Any thoughts about these? You'll have some more practice with these on the homeworks, and of course you will have the opportunity to do this on the test. This is one of our items, is drawing Euler circuits and paths. All right. Great. We have 15 remaining minutes. I think that's enough time to start talking about the next topic on the big list, which is very similar, maybe a little easier. I'm not sure, a little easier. It is no harder, let's say it that way. I am referring to, so the next thing, if you look on our big list, is called minimum, I usually say, minimum duplication circuits or paths. These are similar to Euler circuits, but not quite the same, and they're called minimum duplication circuits. So Euler circuits don't repeat any edges, right? That's the whole point of what an Euler circuit is. It covers all the edges with no repetitions. Euler circuits don't repeat any edges. And this is only possible if all the degrees are even. Only possible when all the degrees are even, all right? But in real life, if you're trying to do this for some reason in real life, if you're like the snowplow guy or something like that, basically that's never gonna be the case. If you just give me like a graph at random, probably the degrees, like some of them are gonna be even and some of them are gonna be odd. There's actually no good reason in real life that all of the degrees will be even. So this Euler circuit is only possible when all the degrees are even. And usually that's not the case. A typical graph just that you draw at random is going to have some mixture of evens and odds. There's no reason in real life that a graph should usually be all even degrees, all right? So Euler circuits, in real life, if I just show you a random graph, probably it does not have an Euler circuit because probably the degrees are some mixture of evens and odds. So this Euler circuit, which don't repeat any edges, these are not always possible. In fact, typically it is not possible. If it's not possible, so if there is no Euler circuit, which is usually the case, if there is no Euler circuit, then we can still try to cover all edges while repeating as few as possible. Right? Euler circuit means you can do them all without any repeats. If you have a graph where that's impossible, what that means is if you want to cover all the edges, you're going to have to repeat some of them. And in that case, you might want to cover all the edges while repeating as few as possible. All right? This is sort of the best you can do if you're the snowplow guy and no Euler circuit is possible. You're still going to think about how can I drive the best possible route, which would be minimizing the duplications, all right? This is called a minimum duplication circuit, which is the name of this topic. Minimum duplication circuit. It is a circuit which covers every edge and repeats as few as possible. Right? Cover all the edges while repeating as few as possible. I'm usually going to write min dup circ just because it's too long to write minimum duplication circuit. All right? For example, here's a very simple example. What if I have a graph like this? All right, look at the degrees as we usually do. They are 2, 3, 2, 3. So here, there is no Euler circuit because there are two odds there. There is no Euler circuit. But I can cover all of the edges with only one duplication. And can I draw that? Here's how I would do it. If I start, say, at the top here, I can go down there, across the middle, back across the middle again, and then up around the edges like that. So this is my circuit with only one duplication. That is, I use that edge in the middle twice. But that's only one that I had to go over twice, all right? So there is no Euler circuit, but that means you must do some duplications. It is possible in this graph to cover all the edges with only one duplication. So this, what I just drew there, is a minimum duplication circuit. All right, it covers all the edges while repeating as few as possible. In this case, it's not possible to do it with no repetitions, but you can do it with only one repetition, like I just did, all right? So what our sort of job for this topic is, how do you figure out, there's kind of two questions at play here. First of all, how do you figure out, like, how many duplications are necessary? In this graph, you can do it by duplicating only one, although in some other graphs, actually this one, so this graph actually is a lot worse. This requires, and we'll talk about how you can figure this out, but just a little preview. This graph requires 4 duplications. So there is an interesting question about when I just show you a graph, how do you even know how many edges I am going to have to duplicate? And then furthermore, which edges am I going to duplicate? Like in this one here, I decided to copy the one across the middle, run across the middle twice. Could I have done it by instead running across, let's say, this edge twice? Actually, it's not possible in that case. You have to know which edges to duplicate. Yeah.
Is there any other edge for that to be possible though?
In this example, actually, this is the only edge that you, every like minimum duplication circuit which duplicates only one edge, it has to be this one.
Okay.
The other ones, it won't work. You can try it out and you'll see. All right, but anyway, all of these questions are things that we're going to try to answer. How would you be able to figure out in this graph, how do you know that this requires 4 duplications? And furthermore, which 4 edges should I plan on duplicating? Actually, in this case, there are many possible different edges to duplicate. In this case, there's only one. But we can, we don't have a lot of time to do this today, but we can get started. Actually, let's just talk about that first one again as a simple example. So here, what is important are these odds. So we look at the odd vertices. And the idea is the best case scenario would be if there's no odds at all. Then I don't have to do any duplications because that's an Euler circuit. You look at the odd vertices and try to double some edges to turn them all even. What I mean by that is double some edges. I see 2 3s here, but if I were to duplicate the edge going across, maybe I'll just draw this in red here. If I double this one up, now these become 4s instead of 3s, right? I don't know if it's clear what I'm talking about. Sorry. If I sort of just add a new edge right there, although it's not entirely new, it's just copying one of the existing edges. If you add a new edge across the middle, those 3s now become 4s. And so after doubling that edge, now all are even. And so that means there is an Euler circuit in the new graph that I made, which has a doubled edge. So we can do an Euler circuit in this new graph. All right. And this is why the edge that you want to duplicate in this one is the one going across the middle, because that's the one which causes these, which used to be odds, to become even. If you had instead doubled up this edge, it wouldn't do anything good. If you think about what the picture would look like if I instead tried to double up this edge right here, it would change that to a 4, but this now used to be a 2 but becomes a 3 after doubling the edge, and I still will have 2 odds. So this is a bad edge duplication because it doesn't actually change all the odds to evens. It gives you change one of the evens to an odd. But this right here is a good edge duplication because it changes all of the odds to evens. This little procedure here, this is called Eulerizing the graph. That is, you duplicate some of the existing edges to make all the degrees even. This is called Eulerizing the graph. You duplicate some of the existing edges to make all of the degrees even. And in the best case scenario, the best way to do this is to pair up the odds and connect them with new edges. So I'm just going to draw a bunch of simple examples. I know it's time to go in a few minutes, but we'll talk more about this next time. For example, here is a graph. How many edges do you need to duplicate in order to Eulerize the graph? So the first thing you should do is find the odd degree vertices, because those are the ones that you should be concerned about. I hope by this point everybody feels good about saying what the degrees of all of these things are. I see 2s in the corners, 4s in the middle, and then all the other ones along the side are all 3, right? That's a 3, that's a 3, that's a 3, a 3, a 3, a 3, a 3, and a 3. Okay, so where are the odd ones? I will just circle the odd ones, as I usually will when I'm doing this. And then, which edges do we need to duplicate in order to turn them all even? My strategy here, which I said, pair up the odds and connect them with new edges. So these odd ones that I've circled, I think they naturally look like you can pair them up. The 2 on the right here, they kind of go next to each other, so I'm going to add a new edge right there. The 2 up top, I can add a new edge right there. The 2 on the side, I pair them up like that, and the 2 on the bottom, I pair them up like that. So now, having added these new edges, all these 3s become 4s. And so that means this graph requires 4 edge duplications. All right. So if you want to do a circuit in this graph that covers every edge, you're going to have to repeat 4 of them. And which ones are you going to repeat? These 4, right? These 4 edges right here. All right, we'll do a bunch more of these on Friday. No homework for today. See you next time.